So the top here, we're going to have essentially theoretical work. People focus on deception processes, theory development, all this stuff, okay? At the bottom, instead, we have applied research, okay? The focus is on methods, how to detect deception, possibly in the field. Now, of course, these two kind of threads have to interact with each other, ideally, okay? But for this panel, I'm going to talk only about some applied stuff, okay? So I want to step back 1 second and talk a little bit about the logic of deception detection. The thing to keep in mind is that we don't really have direct access to deceptive mental states. And so what all methods do, really, is they look for some measurable internal process, either psychological or neurophysiological, depending on your theories, okay, that correlates with deceptive mental states, okay? So what we want to do is we want to postulate an internal process D, okay, such that it's present if and only if the person is in a deceptive mental state, okay? What we do, we can then measure a bunch of variables. This can be behavioral, they can be psychophysiological, or neural variables. We can then perform some statistics on them, some analysis, and try to infer whether the person is in a deceptive mental state or not. Now, of course, all this kind of stuff happens within a particular experimental paradigm, which is actually very important, as I'll say in a second. And in practice, unfortunately, the correlation between this internal process D and deceptive mental states is far from perfect, okay? So there's never one. There is lots of stuff going on and all that. There are countermeasures and all that. And I think the experimental paradigm is actually very important for increasing this correlation, okay? For example, we could use some of the methods that Alder talked about yesterday, for example, by imposing cognitive load and so on. That's where basically the paradigm is very important. Now, different approaches to lie detection vary depending on the internal process they postulate, okay, on the variables that they measure, on the analysis that they carry out on these variables, and of course, on the paradigms that they use. Now, in the traditional polygraphic approach, process D used to be more or less arousal, okay? So people were trying to measure arousal by measuring a bunch of peripheral variables, for example, skin conductance, heart rates, and all that. And from those, they would try to infer whether the person was in a deceptive mental state. It turns out, actually, that some of these peripheral variables are actually very good for distinguishing deception from honest people, okay? Especially skin conductance. So I'm not trying to diminish this approach. I'm just basically saying the way the logic was working. But the neurocognitive approach postulates that this process D is actually a brain process, okay? And the idea is basically to measure a bunch of variables directly from the brain. When I say directly, I mean more or less directly. There is obviously a bunch of steps between the brain and the measures, right? But try to use these measures basically to infer whether the person is in a deceptive mental state or not. Now, the question, of course, is why should we care about the brain at all, okay? We have behavior, we have all sorts of other variables. And I think there are a few obvious reasons, right? The first one is that episodic and semantic memories are stored in the brain, and that's what we use to come up with truthful or deceptive narratives. We use this information. Second, deception also takes place in the brain, okay? That's where the decisions are made and all that. So it makes sense to look there if we can, okay? Third, technologically, nowadays we can record rich spatiotemporal signals from the brain. We can record like tens of thousands of time series, okay? And so the idea is that there must be something in there that allows us to discriminate possibly between deceptive and honest mental states, okay? And there is a difference there with the traditional approach. In the polygraphic approach, what you get is like a single time series, for example, skin conductance, and there is so much you can do with it, okay? So the idea is that by using some sophisticated analysis and machine learning algorithms and all that, perhaps we can come up with some reliable neural signals of deception, okay? That's the idea. Now, how do we record this data from the brain? We have, probably many of you have heard of all these techniques, but nowadays we use some neural measures. The most famous one is EEG, of course, and MEG. We also use some hemodynamic measures, which are a little bit more indirect in the sense that they measure the blood correlates of neural activation, like blood oxygenation, Fmri, and NIRS, especially, okay? These two are the ones that are the most widely used, okay? So that's what I'm going to say, I'm going to talk about today. A couple of things about EEG. You all know about what it is, right? We can collect basically brain signals using these caps. We can collect data from 1 to several tens or even hundreds of channels. And what we do, we get this time series, EEG time series, and we can do a bunch of analysis with this time series, okay? We can collect, on the one hand, we can measure EEG kind of features, okay? Frequency spectra, oscillation, stuff like that, which unfortunately has not been done much so far, mostly because of lack of expertise from the people involved in the field. But we can also, and this is done much more frequently, we can do a bunch of averaging, come up with what are called event-related potentials, ERPs, okay? And make some measurements on these ERPs and see if there are differences between deceptive and honest kind of conditions, okay? In particular, you may have heard about the P300. This is the most commonly used ERP component that is measured and that is roughly an index of recognition, okay? With MEG, we can do the same more or less, but this is not really that much used nowadays for lie detection because it's a really expensive technique, and pretty much you get the same kind of data, really, okay? All right, Fmri, you're probably all familiar with this technique. What we do, basically, we collect a series of brain volumes, okay? Typically hundreds of them. And then we can perform a bunch of statistical analysis, and we come up with these nice and colorful statistical parametric maps that can basically tell you whether some regions, for example, are more engaged or less engaged in one condition than another, okay? We can do exactly the same with NIRS. In this case, NIRS can roughly be thought of as a low-resolution version of Fmri, okay? I think there's a lot of potential for NIRS in the future, but it's not really currently used that much because of some limitations that there are. Okay. So here is some data. These are data from a meta-analysis of pretty much all the Fmri studies that have been done so far on deception. There are about 35 to 40, okay? And what we're showing here is these are maps that show us the difference between deception condition and truthful conditions, okay? So there is quite a bit of consistency across studies when you look at things at this level, okay? And you can see that there are some regions here, including the lateral parts of the prefrontal cortex here and here, okay? Parts in the middle of the prefrontal cortex, right here and here, and parts of the parietal cortex, okay? Now, I'm not going to say much, I'm going to say anything actually about the function of these regions, okay? It has to do with theory, development, and all that. But what I'm going to say is that none of these regions are actually selective for deception, okay? So all these regions are actually engaged by lots of other tasks, okay? Could be like response inhibition, could be memory recall, all of that, okay? But nonetheless, activation in these regions can still be used as a proxy for deception, okay? So in practice, these are average data. When you run a subject in the Fmri, okay, you actually collect data that looks like this, just much noisier, of course. And what we want ultimately is to see if we can use activation in some of these regions and use that to predict or to estimate whether a person is lying or not, of course. So just to give you an idea of how that is done, it's nothing really too complicated, but basically suppose that we have our two groups of subjects. Some subjects are lying, some subjects are telling the truth. And suppose that we are looking at just two regions of interest, a green one and a blue one. And just by using these two regions, we want to see whether we can tell whether somebody is in one group or the other group. And of course, these regions can be large or small, they can be even single voxels, okay? So what we can do, since we have only two regions, we can plot these on a plane. And here on the vertical axis, we plot the activation in this ROI. In the blue axis, instead we plot activation in the blue ROI, okay? And we try to build a classifier that tries to distinguish between deceptive cases and truthful cases, okay? So standard machine learning stuff. And if we vary our criterion, we can actually also come up with, use signal detection theory and come up with these receiver operating characteristic curves that Judith talked about, okay? And we can estimate accuracy of the methods, okay, with the area under the curve, okay? So that's what people have done. And just for those of you who are a bit familiar with the field, in case you've heard of multivoxel pattern analysis, these are just one instance of this general approach. in which the ROIs are really like single voxels, okay? We can do exactly the same with the ERPs and EEG, just that our features are going to be different, of course. They're going to be parts of the time series or amplitude of components and all that. But other than that, the idea is exactly the same. And again, we can estimate our area under the curve. Okay. So where are we? Some of you may have actually read this novel, The Truth Machine, right? It's by James Alpering. I don't know. It's not Shakespeare, but it's kind of interesting, okay? And on chapter 31 here, in this fictional scenario, he says that in 2024, the United States Truth Machine panel officially approved the Armstrong Cerebral Image Processor for use in the nation's judicial system, okay? So in this novel, basically, by 2024, they developed this machine based on some fancy brain imaging technique that is 100% accurate. They solved all the problems with countermeasures, faking, and everything, okay? And it's so good that everybody's using it, and basically it's been introduced in the judicial system itself, okay? So where are we relative to this kind of state of affairs? Well, we're not there, of course, right? So let's start with ERPs. I'm going to focus on accuracy, just because accuracy is a necessary condition for adoption, although not sufficient, of course, right? And most of the work on ERPs has been done with concealed information test, and it's been based on P300 kind of analysis, so very simple paradigms. Laboratory or mock crime studies, so totally not non-field studies, okay? So we are probably overestimating to some extent the accuracy of the methods. And there is like a meta-analysis that was done by Ewood, our volunteer for next year, right? And they found that there is actually quite a large effect size, okay? So it's quite easy to discriminate between deceptive and honest individuals, okay? Or cases, if you do a within subject situation, using ERPs, just using the P300 amplitude, okay? Which is pretty impressive, I would say. And also, in the few studies that I've looked at area under the curve, that's also pretty high. Remember that 1 is perfect classification. Okay, how about fMRI? Same thing, the paradigms are very simple, okay? There is nothing has been done in the field, really. And again, only laboratory or mock crime studies, again. And here, too, the area under the curve is pretty good, okay? It's greater than 0.8. Some studies have actually gone up to very close to 1, okay? So I want to conclude here by saying a few things about, well, first of all, accuracy, okay? So we got this accuracy that is about 0.8, 0.9 area under the curve. How good is it compared to other methods, okay? Now, it turns out that when you look at the literature, actually, is not really superior to that of peripheral measures, okay? So if you look at skin conductance using the same paradigms that have been used with ERPs or with fMRI, you find that the accuracy is pretty close, all right? So the question is, why should we use all these complicated equipment and all that, and why can't you just, stick a couple of electrodes on the fingers and just measure that? I think the reason is that the full potential of neuroscience-based measures has not really fully explored, okay? That's because these methods have been around for a relatively short time compared to skin conductance and all those other measures. And also, basically, as I said before, the signals that we get from these neuroimaging methods, right, are much, much richer than what you get from a skin conductance machine, okay, which is just one time series. So the idea is that we should work more on this, especially on the side of machine learning and statistical analysis, because I believe there is so much more data in there that hasn't been really explored. Okay, so let me conclude with some issues and questions that are important, okay? The first thing I already mentioned is that there have been no field studies, okay? So the question, of course, is, okay, how does all this stuff generalize to anything in the field? Unknown, okay? Also in terms of population, typically these studies use students, basically, not everybody, but typically, all right? The second is that all these techniques basically have very low signal-to-noise ratio, okay? This is not just a problem with neuroimaging. Bruno was telling us about response times. That's why you collect 600 trials, because you want to increase your signal-to-noise ratio, okay? But the question is, if you have to record data for like an hour, okay, is it applicable, okay? Can we really use it for anything real? For example, for Avatar, they probably want to be able to come up with a classification within a few seconds. So you don't have like an hour to test the subject. Also, one issue that is, Bruno talked about that issue, but is a little bit neglected, okay, is that there is recent evidence that cognitive countermeasures, okay, so tricks you can do in your mind, can actually drastically reduce accuracy of neuroimaging measures, okay? It sounds a little counterintuitive because you say, well, how can I change what's going on in my brain? But it turns out that you can play some little tricks in your head and actually fool the machines, okay? So that's one issue that needs to be explored in much more detail. And specifically, we should be able to, if that's the case, we should be able to look for some neural signatures of countermeasure deployment, for example. Okay, then there is also one more issue which has to do with where does the data come from? There are some results, for example, with ARPs. We know that the P300 paradigms are vulnerable to countermeasures, but there are some new paradigms, for example, the complex trial protocol, that seem to be able to beat the countermeasures, okay? The problem, however, is that all the studies on that paradigm come from a single lab, okay? So, okay, they have to be replicated. That's probably a general problem in the field. There has to be much more replication. And I think that's one thing that has to be done in the future. And finally, accuracy, as we saw, is far from 100%. And of course, there's going to be context dependence, all of that. But I think that there is a lot of room there for improvement in all these multidimensional analysis. And I think collaborating with mathematicians and computer scientists will be one thing to do in the future. Thank you.